Hi kids. All right, we have a problem. It says loop. Here's my loop. It's a square loop, 30 centimeters by 20 centimeters. It's moving this way, 3 meters per second, into a magnetic field. As you can see, the magnetic field is right here, directed out of the board. The magnetic field strength is 0.5 Teslas, and we want to determine the current. So I want to figure out how big the current's going to be and the direction of the current induced in the loop if the loop has a resistance of 2 ohms. So there's my problem. This problem is going to relate to Faraday's law. And if you remember, Faraday's law is this. So Faraday's law is the voltage, which EMF, same thing as voltage, is equal to the number of turns, change in flux, divided by the time that change takes. So we're going to have to do a couple things here in this problem, actually a number of different things. First thing we want to do is we want to find the change in flux. If we do change in flux, that's going to be your final flux minus your initial flux. So if we go final flux minus initial flux, flux is BA cosine theta. So my final flux is going to be 0.5 times, that's my B, times the area. Now my area is going to be 0.3 times 0.2, because we got to change that to meters. And then the angle between them is going to be 0 degrees because the direction of the area is always perpendicular to its surface. So if here's the surface, the direction is either pointing straight out of the board or straight into the board, which if I decide it's going straight out, that's exactly the same direction as my magnetic field, so cosine of 0 degrees. So if I do the math there, my final flux is 0.5 times 0.3 times 0.2. I get 0.03 either Tesla meters squared or Webers. And my initial flux right now is 0 because there's no magnetic field. So my change in flux is 0.03 Webers. Okay? So far so good. So let me erase this. So I'm going to have, for my voltage, it's going to be -1, because I have one loop, times 0.03 Webers divided by the time. Now to find the time, we need to figure out how long it takes to completely move into the magnetic field. Well, if it's moving at a constant 3 meters per second, and the distance is this, I can use V equals D over T. So I'm going to get 3 meters per second equals 0.3 meters divided by the time, and I can use this to solve for my time, because that's how long it's going to take to completely move into the field. So if I go 0.3 divided by 3, you get 0.1, and so my time then is 0.1 second. So this is going to be over 0.1 seconds. So if I do the math, you're going to get -0.3 volts. Okay? So that's my voltage, but I'm not done yet, okay, because I still need to figure out the current. Well, luckily I have a Veronese equation, so I'm going to use V equals IR. So I have 0.3 volts equals I times 2 ohms, and if I solve for I get 0.15 amps. So 0.15 amps is going to be the size of the current, but now I need to find the direction of the current. So to find the direction of the current, we're going to use Lenz's law, really, which is what this negative is all about. If you guys remember, a positive or negative with voltage doesn't really mean anything. If you guys measure, when we measure with the meter, you can just switch the leads. It doesn't really mean anything. It's because it's a voltage difference. So if you want to put a negative, that's fine. If you don't, that's okay too. But the negative really tells us that the voltage is going to make a current and this current is going to oppose the change in flux. So this is where I told you guys to do 3 steps. So my first step was to figure out how is the flux changing. So as I move this in, I'm getting more flux and I'm getting more dots. So I would be getting more dots. So that's my first step. The second step was we want to oppose that change. So if I want to oppose that change, I want more dots or I want more X's. Remember, you always take the one where you get more, so I want more X's. That would oppose that change. And then my third step is to use the right-hand rule and figure out which way the current would flow to give me this. So if I want more X's inside it, okay, so I'm going to get X's inside. My thumb's going this way, so then, okay, so it's going around this way. That would be clockwise. Okay, so my answer would be 0.15 amps going clockwise.
Bye, kids.